A function need not have a maximum or minimum on an interval. That's shown in the 3 pictures on the previous page. It says, for instance, figure 4.1a and b, you can see that the function x squared plus 1 has both a maximum and minimum on the closed interval -1, 2, but does not have a maximum on the open interval -1, 2. Moreover, in figure 4.1c, that one with that hole, it says you can see that continuity, or the lack of it, can affect the existence of extrema on an interval. It says this suggests the theorem below. Although the extreme value theorem is intuitively plausible, the proof of this theorem is not within the scope of this text. So in other words, we are not going to prove this, you just need to know this. So what are the conditions? The first condition is it has to be continuous. The second condition is you have to have a closed interval. If that happens, then you have a maximum and you have a minimum. That's what the extreme value theorem says. If you meet these 2 conditions, if your function is continuous and you're considering it on a closed interval, then you can draw the conclusion it has to have a maximum and it has to have a minimum. And it says this is relatively intuitive. So let's think about this. It says in figure 4.2, the graph of x squared minus 3x squared has a relative minimum at the point 0, 0, and that's a relative maximum, I read that wrong, at 0, 0, and a relative minimum at the point 2, -4. Informally, for a continuous function, you could think of the relative maximum as occurring on a hill of a graph, so here's your hill, and a relative minimum is occurring on a valley, like this right here. It says such a hill and valley can occur in 2 ways. When the hill or valley is smooth, rounded, the graph has a horizontal tangent line. So think about horizontal tangent line again. When you have a horizontal tangent line, that means tangent line, that's the slope of the tangent line is the derivative, right? And the slope of a horizontal line is 0. So if you have this smooth graph here, you have a smooth hill or a smooth valley, we know we have a horizontal tangent line, where these are the points where our derivative is equal to 0. Okay? It says when a hill or valley is a sharp-pointed graph, this function represents that it is not differentiable at our high or low point. So a good example of that is the absolute value of x. If you think about the absolute value of x, you think about this point right here, this point 0, 0, that point is a relative minimum. It's a minimum because it is the lowest point in an interval. In fact, that's the absolute minimum as well. It's the absolute lowest point in that in the entire graph. But what they're saying here is, look, think about the derivative at that point. The derivative does not exist at 0. F prime of 0 does not exist. If you remember, the derivative from the left and the derivative from the right don't agree, so the derivative on sharp corners does not exist. So what can we have when we have maximums or minimums? It either occurs where we have horizontal tangent lines, or it occurs at these places which is where the derivative is 0, right? Or it occurs at these places where the derivative does not exist. Okay? So it says, definition of relative extrema. If there is an open interval containing C for which f of C is a maximum, then f of C is called a relative maximum of f, and you can say that it has a relative maximum at C f of C. So, couple of things that I want you to know. You can say, number 1, it occurs when x equals c. So you can talk about a maximum occurring at a given x value. 2, you could say the max or min is, and this right here you're going to put in the y value, or the function value. So the max or min is the actual y value, okay? Or the third thing you can say is it is at the point, and then you would give the ordered pair C f of c, right? Okay, so there's 3 ways that you can answer a question about where's the maximum. You could tell me just the x value. You could give that it occurs at, but you do need to write x equals. You could give me the y value, or you could give me the point. And you have to really read your questions to understand what does this reader care about. When we're talking about a business, for instance, maybe x is the number of shirts and the y value is my revenue. If I want to maximize my revenue, I might want to know each one of these things individually. I might want to know the x value, which would be the number of shirts I need to produce, and I also might want to know the y value, which would be the maximum revenue that I could make. So each one of these things has individual meaning, and you need to understand what the question is asking. Does the question want the x value, the number of shirts, the y value, the revenue, or does it want the point, which gives us both of them? So I usually err on the side of caution and give the point because that makes both questions answered. But in application problems, they're going to ask for a specific answer, and you're going to need to interpret those, okay? And that's what this is getting at here. It says f of c is the maximum, so the y value is the maximum, okay? But you can say it has a maximum at that point. So if you're thinking graphically, it's a point. The y value is the maximum, but it occurs at that point. So they're just telling you there's different ways that you can write it. I also do want to let you know that they use the term relative. Relative is the same thing as local. So if you see anyone say find the relative extrema or find the local extrema, they're saying to find the same thing. Don't worry about that. They give you the exact same definition with the relative minimum, just saying it's the lowest point. Okay, it says the plural of relative maximum in relative is relative maxima, and the plural of relative minimum is relative minima. And it says relative maximum and relative minimum are sometimes called local maximum and local minimum. So there it is right there. Relative is local.